Hi guys, so we're going to talk about rational functions, and I'm probably going to break this into two different videos because this is going to be kind of lengthy. Um, so let's start with vertical asymptotes. Remember, these are your type of functions that look like this. So, I mean, that's the most basic form, but um, with that being said, this obviously presents some issues in terms of domain because if the bottom x is actually equal to 0, you know that you cannot divide by 0, and that would be the case where this does not have a value for 0. And so this determines whether there is a whole or a asymptote. An asymptote is basically an invisible line that the graph approaches infinity at that point in some direction. And so for 1 over x, remember if I draw the y-axis, the y-axis, it looks like this. This is where x is equal to 0. And since it has no value, what this graph actually does is it comes up and it goes up towards positive infinity here. And it goes something like this, and it goes down towards negative infinity on this side. And then it also has more asymptotes going on the x-axis in this case, and we'll talk about that more later. But what your goal is to find out the domain of these things, and since it's the domain, you only really have to check where the bottom is equal to 0. Now, a hole happens when the graph does something like this. It approaches that point, and it doesn't necessarily have an asymptote there, and I will explain to you why that happens or how to know that that's happening, and I'll show you at the next couple of examples. So, it's pretty simple to know when there's a hole or when it's an asymptote, as long as you can figure out what the asymptotes are. So for part A, let's look at it. We're looking here. We have x squared minus 9 over x minus 3. Okay. So the top factors, right? This is x plus 3, x minus 3 over x minus 3. Now, notice that this cancels with this. Okay, so it gives us x plus 3. So what that means is this is actually a whole and not a asymptote. And obviously you notice that x cannot equal 3 in this case, because if x is 3, this is 0. So by plugging in 3, you have a whole, but if what we're going to do is we're just going to graph x plus 3, which is the line that goes through 3, and it goes up 1 over 1, so it goes here, and we just kind of draw a line. But the only thing is, when we get to 3, we go up 1 over 1, and then I need more room. Up 1 over 1. Here there's a hole. So it hits that hole, and then it keeps going. And what the hole represents is that there's no value there, because if you take the original function and plug 3 into it, you'll see that you cannot divide by 0. But it's not necessarily the case that that 3 makes it shoot off in any direction towards infinity. The points relatively close to that on the left of 3, like 2.99 and 3.001, they're still very close to 3, and rather than getting closer and closer to infinity, they don't make the graph shoot up high or low or whatever is going to happen. So how you know it's a whole is when something cancels. If you can cancel something after factoring, you know that this is a whole. So let's look at B. We have x over x squared minus 9, which we just said was x plus 3, x minus 3. Now, if I asked you what the domain is, notice nothing cancels here. Well, you're going to tell me x cannot equal 3 and x cannot equal negative 3. So what does the domain look like? Well, then we go from negative infinity, look at a number line. Say negative infinity is over here, positive infinity is over here. Somewhere in here is negative 3, somewhere over here is 3. It can't equal this number. It can equal anything else, and it can't equal 3 and anything else. So if you look, it goes from negative infinity to negative 3. Okay, skip negative 3. So we jump from the left side of negative 3 to the right side. We go up to 3, skip it, just like we just did with negative 3. left side, right side. And then we go to infinity. And this is the domain of this thing. So if we were to draw this graph, we're going to go to -3, 1, 2, 3. We're going to draw a vertical asymptote. 1, 2, 3. We're going to go to 3 and draw a vertical asymptote. And then we can kind of figure out what we need to do to graph this. Just a hint, x equals 0 is a point on this because if I plug 0 in, notice that the top is 0, and that's when 0 out of whatever the number is going to be 0. And so this will actually cross through this. It'll either make like a x cubed, or it will either do, well, still x cubed, but it'll either do that or that, one of the two. So there's that. And then let's look at the next one. We have x plus 3 over x squared plus 9. And if we tried to solve this one, does this factor? That's the first question. No. Okay, so then what's the domain of this? Well, it turns out it's negative infinity to infinity because this is never 0. This is the graph x squared plus 9. So you go up to 9, you put a parabola, and it goes like that. Well, notice that it never equals 0. It never crosses the x-axis. And therefore, any number that you plug in for the domain of this will not make this bottom 0, and therefore the domain is from negative infinity to infinity. Okay, so let's just recap real quick. Look at the denominator. If the factors parts cancel, then it is a hole in the graph where the denominator piece is equal to 0. If the factor part does not cancel, then that is now an asymptote. Okay. Now let's talk about horizontal asymptotes. So we've got degrees. So we have the degree of the numerator. Let's call the degree of the numerator n, and let's call the bottom m. If degree n, degree of the numerator, is greater than degree denominator, then, I guess I'll write then no horizontal asymptote. Okay, so what that means is you're going to look at the degree of the numerator. So if you have x to the fifth over x squared minus 2, for instance, then you can assume there is no horizontal asymptote. That means there's no point where this just shoots off towards infinity going left and right. Okay. So notice the degree here is 5, the degree here is 2. Okay. If the degree of the numerator is equal to the degree denom, then horizontal asymptote is a ratio at y is equal to a over b. Now let me define a over b for you because I forgot to do that. So if we have x to the n a and b x to the m, then it's just the lead coefficients from these two things. Okay, so you just make a fraction out of them and you figure out what the asymptote, where it's at. Okay, and then finally, if degree numerator is less than degree denom, then, I don't know why I wrote then horizontal asymptote, I don't know why I spelled that horrible, what? Is at y is equal to 0. Okay, so it's always y is equal to 0 if that's the case. One other thing to note about this for the top one, if its degree numerator is greater than so what I want to say is if the degree is exactly one bigger, then it's a slant asymptote. If the degree of numerator is exactly one higher than denom, then there is a slant asymptote. Okay, now to find that slant asymptote, you have to use long division, and what you get in the division for the remainder, I believe, is your slant asymptote. I will verify that. It's been a while since I've taught this, but I'm pretty sure it's where your remainder is. I will clarify this for sure in the next video because I'm going to stop it here. We've talked about the asymptotes. We'll actually do a demonstration of these next, and then we'll move on from there. So there's quite a few parts to this. This is just the first part, so hang in there. Make sure you take notes on these slides. I hope this is helpful. Thank you, guys.